everyone, and welcome to Lecture 8 of the AI Robot Systems course. Today's topic is Vehicle States, Dynamics, and Simulation. In this lecture, we'll move beyond reactive control methods and start to explore how a vehicle's motion can be mathematically modeled and simulated. Understanding these dynamics is fundamental for autonomous driving, because every control command, whether it's steering or throttle, directly affects the vehicle's state in space, including its position, velocity, and heading. Our main objectives for this lecture are threefold. First, to understand the core vehicle states: position, velocity, yaw, steering, and slip. Second, to learn how to model vehicle dynamics, starting from the basic kinematic equations and progressing toward nonlinear and multi-body models. Finally, to connect these state equations to real-world sensing, simulation, and control frameworks that allow us to predict and influence vehicle behavior. Let's begin with an overview of today's lecture. We'll first discuss vehicle states, which describe how we mathematically represent a car's motion, things like position, velocity, and orientation. Next, we'll move on to vehicle dynamics modeling, where we express how control inputs, such as steering or acceleration, cause changes in those states. Finally, we'll talk about vehicle dynamics simulation, showing how these models can be used in practice to predict and visualize vehicle motion. Now let's begin with the concept of vehicle states. Every moving vehicle has a set of quantities that describe how it currently is. These include where the car is located, which direction it's facing, and how fast it's moving. In control and simulation, we call these quantities the state variables of the vehicle. The first component of a vehicle state is its position. Position defines the translation of the vehicle in a certain coordinate frame, either global or local. It's often expressed relative to the vehicle's center of gravity or a predefined base frame. In practice, we usually use X and Y coordinates measured in meters. For example, on the track shown here, the car might be at X equals 2.5 meters and Y equals 3.8 meters. Next, let's talk about heading, which defines the rotation of the vehicle. Heading describes the orientation of the car relative to the x-axis of its coordinate frame. It tells us which direction the vehicle is facing at a given moment. Heading can be expressed as a single angle value. For example, we can use radians from minus pi to plus pi, which corresponds to minus 180 to plus 180 degrees. Or from 0 to 2 pi, that is 0 to 360 degrees. This orientation can also be represented in different mathematical forms, such as roll, pitch, yaw, rotation matrices, or quaternions. This slide visualizes how heading angles are represented on a circle. On the left, we see the range from 0 to 2 pi. That's the full circle of 360 degrees. On the right, we see the alternative range from minus pi to plus pi, which is from minus 180 to plus 180 degrees. Notice that the direction of rotation is positive when turning counterclockwise and negative when turning clockwise, a convention used in robotics and vehicle dynamics. Next, let's move from global coordinates to a more track-oriented coordinate system called the Frenet frame. The Frenet frame is a moving coordinate system that travels along a curve. It's defined by the tangent line and the curvature of the path. Mathematically, this frame is spanned by three vectors: a tangential vector t, a normal vector n, and a binormal vector b. This coordinate system is defined by three vectors. First, the tangential vector t represents the instantaneous direction of motion along the curve. It points forward along the track, showing where the vehicle is currently heading. Second, the normal vector n is perpendicular to the tangential vector. It indicates how far the vehicle moves sideways, describing the lateral offset from the track's center line. Finally, the binormal vector, B is obtained as the cross product of T and N. It points vertically upward from the track surface, defining the orientation of the plane on which the vehicle moves. Together, these three, T, N, and B, form a set of mutually perpendicular axes, creating an orthogonal coordinate system that moves smoothly along the curve. This Frenet frame allows us to describe the vehicle's position and orientation relative to the track in a much more intuitive way. In two-dimensional motion, the Frenet frame can be simplified to just two coordinates, S and D. The S coordinate represents the vehicle's progress along the reference path. You can think of it as the distance you've traveled along the track's centerline, measured from the very beginning, where S equals 0. As the car moves forward, the S value keeps increasing, just like the odometer reading in a car. It's a curvilinear distance that follows the shape of the path, not a straight line. On the other hand, the D coordinate describes the lateral offset, that is, how far the vehicle is from the reference path sideways. When the car is perfectly on the center line, D equals 0. If the car moves to the left side, D becomes positive, and if it moves to the right side, D becomes negative, following the right-hand rule convention. In short, S tells us how far the car has gone, while D tells us how far it is from the center line. Together, they form an intuitive and compact way to describe motion along a curving track. Now, let's see how the Frenet frame is used in practice. On the left side of the slide, we can see the distance to the center line. This value tells us how far the vehicle is laterally offset from the middle of the track, measured in meters. For example, if the lateral coordinate D equals minus 0.8 meters, that means the vehicle is 0.8 meters to the right of the center line. When the car drifts slightly to the left side of the lane, D becomes positive. And when it moves to the right, D becomes negative, following the right-hand rule we learned earlier. On the right side, we see the progress along the track, which is represented as an ordered list of waypoints. Each waypoint stores its own x, y coordinates in the global frame. By connecting these waypoints in order, we can reconstruct the entire trajectory of the track. In a closed-loop track, the first and last waypoints are the same, creating a continuous loop that allows the vehicle to run lap after lap. In simulation and path planning, this Frenet representation is extremely useful. It converts the complex geometry of a curved track into two simple variables, S and D, making the control and prediction process much more intuitive. Finally, let's talk about linear velocity and acceleration, two of the most fundamental quantities that describe how the vehicle moves. Linear velocity tells us how fast the vehicle's position is changing, while acceleration tells us how fast the velocity itself is changing over time. These values are measured along the x and y axes, and sometimes also along the z axes, depending on whether we consider two-dimensional or three-dimensional motion. In ground vehicles, we usually divide motion into two components: longitudinal motion, along the direction of travel, the x-axis, which represents forward and backward movement; lateral motion, perpendicular to it, the y-axis, which represents sideways movement, such as lane changes or cornering. These quantities can be measured using various sensors, such as GPS for global velocity, IMU for acceleration and orientation, wheel speed encoders for local ground speed, or pidosensors in aerodynamic testing for airflow-based measurements. Velocity is typically expressed in meters per second, written as m/s, while acceleration is expressed in meters per second squared, written as m/s squared. It's also important to remember that the direction convention of each axis follows the right-hand rule, which ensures consistency between position, velocity, and acceleration vectors in the vehicle's local coordinate frame. Now we move from linear motion to rotational motion about the car's center of gravity. We describe rotation with angular velocity, written omega, and angular acceleration, written alpha. Around the x-axis, the motion is roll. That is side-to-side tilting of the chassis, with omega x and alpha x. Around the y-axis, the motion is pitch. That is the nose moving up and down, with omega y and alpha y. Around the z-axis, the motion is yaw. That is the car turning left or right, with omega z and alpha z. Together with translational motion in x, y, and z, these rotations form a 6-degree of freedom model. We usually measure angular rates with the IMU gyroscopes and linear accelerations with accelerometers. Remember that accelerometers sense specific force, so gravity is included. We remove it by calibration or filtering. Use a consistent right-hand roll for axis directions, so the sign of roll, pitch, and yaw is unambiguous. Finally, note the link to control. Large lateral accelerations often correlate with large yaw rates, and roll and pitch transients tell us about weight transfer and grip. Interpreting these signals helps us diagnose understeer, oversteer, or poor damping. Next is the steering angle, delta. Delta is the angle between the front wheel direction and the vehicle's x-axis, the forward axis. In simplified bicycle models, we use one common steering angle for both front wheels. Units can be degrees or radians, but be consistent with your controller and logs. Geometrically, steering sets the road curvature. For small angles, we use curvature kappa is approximately tan of delta divided by wheelbase L, and the yaw rate is approximately speed times curvature. In practice, delta saturates due to mechanical limits, and the actual path also depends on tire slip. Therefore, we calibrate the steering sensor, keep a clear sign convention, left positive or right positive, and always log delta with speed and yaw rate to check the model match. When a vehicle moves fast, its tires don't always roll perfectly in the same direction as the car's body. We call this difference slip, and there are 3 key forms. First, the side slip angle beta. This appears when the whole car drifts sideways. The car's velocity vector is no longer aligned with its x-axis. Second, the tire slip angle alpha, which happens at each wheel. It is the angle between the tire's actual rolling direction and the direction of travel. This slip angle alpha is what generates the lateral tire force, the force that allows cornering. And finally, the wheel slip ratio S, which appears when the tires spin faster or slower than the actual vehicle speed, for example, during hard acceleration or braking. Together, these slip measures explain why drifting cars can still be controlled and why traction is so critical. So how can we actually measure these vehicle states in practice? We rely on multiple sensors. The most common one is GPS, or Global Positioning System, which gives us the vehicle's absolute position on Earth. Next, we use odometry sensors, such as gyrometers or wheel speed sensors, which provide information about rotation, orientation, and travel distance. We can also use cameras or LiDARs, which observe the environment visually or by laser scanning. Sometimes a single sensor provides partial data, so in practice, we often fuse several sensors to get an accurate vehicle state estimate. Finally, one of the most important engineering skills, visualizing your vehicle states. Don't just look at single numbers. Plot the data to reveal trends. By comparing velocity, heading, or steering angle over time, you can detect anomalies such as oscillations or sudden spikes. Visualization tools like Plot Juggler, Matplotlib, or RQT-Plot help us analyze performance, calculate errors, and interpret signals correctly. A good engineer doesn't just collect data. They learn to understand its meaning through visualization. Now that we've learned what vehicle states are and how to measure them, let's move on to a deeper question. Why do we model vehicle dynamics? This section, Vehicle Dynamics Modeling, will show how we can mathematically describe how a car moves, turns, and reacts to inputs like steering or acceleration. By the end of this part, you'll understand not only how cars behave, but also how we can predict that behavior using simplified equations. Prediction is important in multi-age English. Let's start with a simple question. Which trajectory is the car following, A, B, or C? At first glance, it looks like the car might be following path B. But actually, we cannot be sure just by looking at its position. To know exactly which trajectory the car is following, we need more information, such as its velocity, acceleration, and steering angle. We also need to know physical parameters of the car itself, its mass, length, and width. Without these, we can't predict how the car will respond to inputs or forces. That's why we need a vehicle dynamics model to connect what we see with how the car truly behaves. To understand modeling, think about a car as a dynamic system. It receives inputs such as the steering wheel angle or motor torque. Then it produces outputs such as speed, acceleration, or turning behavior. In between, we can build a simplified representation of the car, a mathematical model that approximates the real vehicle. This model is called the Vehicle Dynamics Model. It is typically defined using differential equations or characteristic curve correlations that capture how the vehicle responds to forces and inputs. Of course, the model can never be perfect. There is always some mismatch between simulation and reality. But the better our model represents the physics, the more accurate our predictions and control become. Let's now take a closer look at what we call system dynamics, the mathematical way to describe how a system behaves over time. A dynamic system can be described as a relationship between two main signals, an input denoted by U and an output denoted by Y. This relationship is often expressed using ordinary differential equations, or ODEs. Inside this system, we have a set of state variables written as X. These states represent the internal condition of the system. For example, in a car, X could include the position, velocity, or heading angle. The standard form of the system can be written as x dot equals A times X plus B times U, and Y equals C times X. Here's what each term means. A, the system matrix, defines how the internal states influence each other. B, the input matrix, describes how the inputs affect the system. C, the output matrix, defines what part of the internal state we can actually observe or measure. Together, these equations describe both parts of the system. The system dynamics equation, which shows how states evolve over time based on inputs and initial conditions, and the output equation, which links those internal states to the observable outputs. In summary, this is the mathematical foundation of all dynamic models, from simple mechanical systems to complex vehicle dynamics. Now let's simplify our general model into a linear form, which is much easier to analyze and simulate. In a linear system, we can approximate the relationships using constant matrices, A, B, and C. The state equation becomes x dot equals A times X plus B times U, and the output equation becomes Y equals C times X. Here, A is the system matrix, which defines how the states influence each other. B is the input matrix, which defines how the inputs affect the states. And C is the output matrix, which defines what we can measure from the states. Now, sometimes we include time t explicitly in the equation, and then it looks like this. X dot equals f of x, u, and t. This means that the system's behavior changes over time. For example, when the road condition, tire friction, or vehicle mass changes as we drive. In that case, we say the system is time varying if the matrices A and B remain constant, independent of time. The system is called time invariant. That's the simpler and more common case we use for control and simulation because it allows us to predict the vehicle's response more easily. So, to summarize, the first form without time assumes a fixed system, while the second form with time accounts for environments or parameters that evolve dynamically. Now let's look at different types of vehicle dynamics models, starting with traditional analytical models. On this axis, we can see that as the number of parameters increases, the accuracy of the model also increases, but so does the complexity and the required computation. At the simplest level, we have the single-track model, also called the bicycle model, which assumes that the left and right wheels can be combined into one track per axle. It's widely used in autonomous driving and control because it's simple but still accurate enough. Next, the double-track model adds left and right wheel dynamics separately. This gives better precision, especially when the car is turning or braking unevenly. After that, we have multi-body simulations, which include detailed suspension, steering, and drivetrain components. Finally, at the highest level of detail, we reach finite element simulations, which model the physical deformation of individual parts, for example, the chassis or tire contact patch. These are very accurate, but they require enormous computational cost, so they are used mostly for offline analysis and design validation. So in summary, as we move from left to right, we gain accuracy but lose real-time feasibility. That's why we often choose the right level of abstraction depending on our goal: control design, simulation, or hardware validation. So far, we focused on physics-based analytical models, but with the rise of machine learning, new types of vehicle models have emerged: data-driven and hybrid models. On the left, we have the analytical model, where the next state is computed entirely using a physics engine. Here, the parameters theta am come from physical laws and equations of motion. Next, the data-driven model relies purely on data. It learns the mapping from the current state to the next state using a neural network with parameters theta nn. However, since it lacks physical constraints, it may behave unrealistically outside the training data. To combine the best of both worlds, we use residual physics models. In this approach, we start with a physics engine, then let a neural network learn only the remaining errors, the small residuals that physics alone couldn't capture. Finally, the hybrid model tightly integrates the physics and neural components into a single simulator. Here, both theta am and theta nn are learned jointly, allowing the model to remain physically interpretable, yet flexible and data adaptive. This hybrid approach is now becoming popular in modern autonomous driving research because it balances accuracy, interpretability, and data efficiency. Now let's begin our discussion of single-track models, also called bicycle models in vehicle dynamics. These models are fundamental because they represent the essential behavior of a car using a very simplified structure. Even though they look simple, they are powerful enough to capture most of the lateral and longitudinal motion needed for control and simulation. The single-track model relies on a few simplifying assumptions. First, wheels on each axle are combined into one equivalent wheel. That's why it's called a single track. Second, the center of gravity is assumed to be located at the road level. Third, there is no rolling or pitching motion, meaning we only consider motion in the XY plane. Fourth, we ignore wheel load differences between left and right sides. Finally, there are no vertical dynamics, so effects like suspension compression are not modeled. These simplifications make the model very efficient for control and simulation, while still preserving the essential 2D behavior of the car. Now let's take a closer look at the kinematic single-track model. This model focuses on geometry and kinematics rather than on the actual physical forces acting on the vehicle. In other words, it completely ignores tire dynamics, so there are no lateral forces, no lateral accelerations, and no slip angles involved in this model. Let's take a moment to explain what these terms really mean. First, the lateral force is the sideways frictional force generated by the tire when it resists sliding during a turn. Imagine your car going through a curve. The tires push sideways against the road surface to counteract the outward centrifugal force. That sideways friction is the lateral force. Next, the lateral acceleration is the sideways acceleration that comes from those lateral forces. It's what you physically feel when your body leans outward while cornering. If you've ever felt yourself pushed toward the door while taking a sharp turn, that's lateral acceleration in action. Finally, the slip angle is the small difference between the direction your tire is pointing and the actual direction your vehicle is moving. Even though the tire is rolling forward, the friction causes it to slightly twist relative to the direction of travel. That angle difference is called the slip angle. But in a kinematic model, we ignore all of that. We assume the tires roll perfectly without any sliding or deformation. The car moves smoothly across the ground as if it were gliding on rails, completely free of any side forces or tire slip. This simplification makes the equations much easier to handle, and it's accurate enough for low-speed scenarios such as lane following, parking, or precise path control. Now, let's talk about the Ackermann steering principle. The Ackermann geometry assumes that all wheels rotate around a single instantaneous center of rotation. That means, during a turn, each wheel traces a circular path with a slightly different radius, but all of those circles share one common center point. This ensures that the tires do not slip or scrub against the road during cornering. It's a key design concept used in real cars to minimize tire wear and achieve smooth, efficient steering, especially at low speeds. Now let's interpret the diagram on this slide to better understand what the kinematic single-track model really describes. You can see a simplified vehicle represented by two wheels on a single line, one front wheel and one rear wheel. This is why it's called a single-track model. In reality, a car has four wheels, but here, the left and right wheels of each axle are combined into one. The front wheel is shown at an angle delta, which represents the steering angle. When the vehicle turns, this wheel defines the direction of motion. The vehicle's overall motion can be described using its velocity vector v, which is aligned with the car's heading direction, shown as the angle psi. So psi represents how the car is oriented relative to the XY coordinate frame. The distance between the front and rear wheel is marked as L sub WB, which stands for wheelbase length. That's the key geometric parameter of this model. Now, since this is a kinematic model, we completely ignore the complex tire forces and deformations. In this view, the tires simply roll without slipping, so there are no lateral forces, no lateral accelerations, and no slip angles. As a result, the vehicle's path is determined purely by its steering geometry. We assume that the front and rear wheels both follow circular paths around the single instantaneous center of rotation. Shown in the figure as a point outside the car's path, this concept follows the Ackermann steering principle. All wheels are aligned such that their extended axes intersect at this single point. This assumption works very well at low speeds or tight turns, where tire slip is minimal. That's why this model is often used for path tracking, parking, or autonomous control in slow motion scenarios. To summarize, the kinematic single-track model is a simplified two-dimensional representation of vehicle motion. It ignores the physical forces and focuses purely on geometry. Even though it's simple, it serves as a strong foundation for path tracking, control design, and the early stages of autonomous vehicle development. Now, let's describe the state variables and equations of the kinematic single-track model. We define 5 state variables. x1, the vehicle's position along the x-axis. x2, the position along the y-axis. x3, the steering angle delta. x4, the velocity v. And x5, the heading angle psi. There are 2 input variables, u1, the steering rate noted as v delta, and u2, the longitudinal acceleration noted as a long. Now, the state equations are as follows. x1 dot equals x4 times cosine of x5. x2 dot equals x4 times sine of x5. x3 dot equals f steer of x3 and u1. x4 dot equals FACC of x4 and u2, and x5 dot equals x4 divided by LWB times tangent of x3. Here, LWB represents the wheelbase of the vehicle, the distance between the front and rear axles. So, the yaw rate, or how fast the vehicle rotates, depends on the vehicle's velocity and steering angle. Now, let's think about what it really means when we say that these state equations are written as ordinary differential equations. Each state variable, such as position, velocity, or heading, changes continuously over time. The differential equations describe how fast those values change at any given moment. For example, x1 dot equals x4 times cosine of x5 means that the x position changes depending on the velocity and heading direction. The dot above x means the rate of change with respect to time, how fast the state increases or decreases. So, these equations don't give the values directly, but rather describe how the state evolves over time as the vehicle moves. When we simulate this system, we integrate these equations step by step, predicting the next position, velocity, and heading. That's how dynamic models can capture continuous motion and produce realistic vehicle behavior. Even though this model looks simple, it is one of the most widely used in path tracking and motion control because it clearly connects geometry, steering, and vehicle motion. Before we move on, let's ask an important question. Why do we now call this model dynamic? In the previous kinematic model, we only described geometric motion, how the vehicle moves based on its steering angle and velocity. There were no forces or masses involved. It was purely about geometry and motion, which works well only at low speeds or gentle maneuvers. But in reality, vehicles experience forces. The tires generate lateral and longitudinal forces, and the vehicle has mass and inertia that resist changes in motion. Once we start considering these physical quantities, forces, mass, acceleration, and tire stiffness, we are now following Newton's laws of motion. That's why we call it a dynamic model. The dynamic single-track model allows us to explain why the car moves the way it does, not just how it moves. It connects the vehicle's geometry with the underlying physics of forces and momentum. Now, let's move on to the dynamic single-track model with a linear tire model. Up to now, our kinematic model ignored the tire forces, but in reality, tire forces play a major role in how a vehicle turns and stabilizes. This dynamic model considers important effects such as understeer and oversteer. To describe these effects, we must include tire dynamics. The tire can generate two main types of forces: lateral forces, which act sideways during cornering, and longitudinal forces, which act along the direction of motion, for example, during acceleration or braking. The amount of force a tire can produce depends on the friction coefficient, usually denoted by the Greek letter mu. A higher friction coefficient means the tire can grip the road better and apply greater force without slipping. In the linear tire model, we assume a linear relationship between the tire's lateral force and the side slip angle, which is the small angle between the tire's actual pointing direction and its direction of travel. This relationship is represented using the cornering stiffness, denoted by capital C or sometimes C sub S. The cornering stiffness tells us how sensitive the tire force is to small changes in the side slip angle. So, when the side slip angle increases slightly, the lateral tire force also increases proportionally, as shown by the straight red line on the right-hand graph. In summary, the linear tire model adds realism to the vehicle's dynamic behavior. It allows us to study how steering inputs, tire grip, and speed together influence the vehicle's stability and cornering performance. Now, let's take a closer look at the linear tire model and see how tire forces are generated. On the left, you can see a tire coordinate system. Here, the tire experiences several different forces: a longitudinal force, labeled F sub x, a lateral force, labeled F sub y, and a normal force, F sub z, which acts vertically from the ground. When the tire is not perfectly aligned with its direction of travel, a small slip angle, denoted alpha, appears between the wheel's heading direction and its actual velocity direction. This slip angle is what generates the lateral tire force F sub y. The larger the slip angle becomes, the greater the lateral force, up to a certain limit. Now, look at the graph on the right. The horizontal axis represents the slip angle alpha, and the vertical axis represents the lateral force F sub y, in the linear region shown by the straight rising part of the red curve. The tire force increases proportionally to the slip angle. This is why we call it the linear tire model. The slope of this linear region is called the cornering stiffness, denoted as C sub alpha. Mathematically, it is defined as C sub alpha equals F sub y divided by alpha. This means that for a small change in the slip angle, delta alpha, the lateral force changes by delta F sub y, and the ratio between them is the cornering stiffness. However, as the slip angle becomes larger, the tire begins to saturate and the relationship is no longer linear. The tire cannot produce additional lateral force beyond its grip limit, and the curve starts to flatten or even decrease slightly. In summary, the cornering stiffness represents how strongly the tire resists lateral slip. In the linear region, this relationship is predictable and easy to model, but beyond that, nonlinear effects dominate. And that's what motivates more advanced tire models, such as the Paseka magic formula, which we'll explore later. Now, let's look at the dynamic single-track model with nonlinear tire dynamics. Don't worry, the equations look long, but we'll focus only on what's physically happening, not the math details. This model expands upon the linear tire model we saw earlier. Previously, we assumed that tire forces increase linearly with the slip angle. But in reality, tires behave non-linearly, especially when the slip angle becomes large. For example, during hard cornering, drifting, or sudden braking. So this model includes non-linear tire forces. That means the lateral forces at the front and rear tires, denoted as F sub SF and F sub SR, are now calculated using non-linear tire models such as the Paseka magic formula. This allows the simulated vehicle to behave much more realistically. Let's review what each variable means. x1 and x2 are still the vehicle's position coordinates. x3 is the steering angle. x4 is the forward velocity. x5 and x6 represent the yaw angle and the yaw rate, which describe how fast the vehicle is rotating. A new variable, x7, called beta, represents the side slip angle, the angle between the car's velocity vector and its body axis. It captures how much the car slides sideways. Finally, x8 and x9 represent the rotational speeds of the front and rear wheels. These are important for modeling braking torque and engine torque, which directly affect traction and stability. Now, among all these equations, two are particularly important for vehicle dynamics. The ones for x6, the yaw rate, and x7, the side slip angle beta. Let's start with x6, the yaw rate. It tells us how fast the car is rotating around its vertical axis. This equation is derived from rotational dynamics, which states that the rate of change of yaw rate is equal to the net yaw moment divided by the yaw inertia. In practice, this moment is generated by the difference in lateral forces between the front and rear tires. If the front tires create more lateral force, they produce a turning moment that increases rotation. This is called oversteer. If the rear tires dominate, the car resists turning. That's understeer. The balance between these two determines whether the car feels sharp or stable in a corner. Next, let's examine x7, the side slip angle beta. This describes the angular difference between the direction of travel and the vehicle's heading. It changes due to two effects, the yaw rotation and the lateral tire forces. When the car yaws, the body direction changes faster than the motion direction. This alters beta. At the same time, lateral tire forces push the vehicle sideways, which can either increase or decrease beta depending on their direction. So, the differential equation for beta balances these two influences, the rotational term from the yaw rate and the translational term from the lateral forces divided by the vehicle's mass and velocity. In short, x6 describes how fast the vehicle rotates, and x7 describes how much it slides while turning. Together, they determine the car's cornering stability. Overall, all 9 state equations represent Newton's laws of motion for both translation and rotation, combining the effects of mass, yaw inertia, and the nonlinear tire forces acting on the vehicle. So instead of memorizing these equations, what's more important is understanding the flow. Steering angle changes the slip angle. Slip angle determines the tire forces. Tire forces create yaw motion and lateral acceleration. And all of these define how the vehicle turns and stabilizes. This nonlinear single-track model is the foundation for realistic simulators and modern control algorithms such as electronic stability control and model predictive control. Now, let's move on to the dynamic single-track model with nonlinear tire dynamics. This model is based on the single-track model with linear tire behavior, but it removes many of the simplifying assumptions we used before. In the linear tire model, we assume small slip angles and a simple linear relationship between tire force and slip. However, in real driving, especially during sharp turns, acceleration, or braking, this assumption no longer holds. The tires behave non-linearly. In this nonlinear model, we include both lateral and longitudinal tire forces for the front and rear wheels. We no longer use small angle approximations. Instead, the tire forces now depend on the full slip angle and slip ratio. The relationship between the lateral force F sub y and the slip angle alpha is now nonlinear. As shown in the graph on the right, the force increases with alpha at first, but then saturates when the tire reaches its grip limit. To describe this nonlinear behavior, we use empirical tire models such as the Pacheco magic formula or the Fiala model. These models fit real tire data mathematically, allowing us to simulate how the forces evolve with slip and load. Now let's see how this affects the vehicle dynamics. The nonlinear single-track model extends the previous equations to include realistic tire forces, side slip, and wheel rotation. We define the following state variables. x1 and x2 are the vehicle's position coordinates. x3 is the steering angle delta. x4 is the forward velocity. x5 is the yaw angle, and x6 is the yaw rate. That is, how fast the vehicle is rotating. The new state, x7, called beta, is the side slip angle. It represents the difference between the vehicle's heading direction and its actual motion direction. In other words, how much the car is sliding sideways. Finally, x8 and x9 represent the rotational speeds of the front and rear wheels. They're needed to model braking torque, engine torque, and traction. Among these states, the most important are x6 and x7, the yaw rate and the side slip angle. Let's start with the yaw rate equation. x6 dot. It comes from rotational dynamics. This means it calculates the yaw acceleration from the difference between the front and rear tire forces, each multiplied by their lever arms, L sub F and L sub R. This captures important effects like understeer and oversteer, depending on which tire dominates. Next, the side slip equation, x7 dot, describes how the vehicle slides laterally while turning. It's influenced by both yaw motion and tire forces. The first term comes from the yaw rate. As the vehicle rotates, the heading changes faster than the actual velocity direction. The second term depends on the tire forces divided by the vehicle's mass and speed, which cause the vehicle to slide sideways. In short, x6 determines how fast the car rotates, and x7 determines how much it slides. Together, they describe the essential dynamics of vehicle stability. So rather than memorizing these long equations, it's more meaningful to understand the cause and effect chain. Steering changes the slip angle. Slip angle changes the tire forces. tire forces create yaw motion and side slip, and those together define how the vehicle behaves in corners. This nonlinear single-track model is the foundation for high-fidelity vehicle simulations and advanced control algorithms, such as electronic stability control or model predictive control. Now, let's move on to the multi-body vehicle model. This model goes beyond the single-track approximation and represents the vehicle as a combination of multiple components. Here, each wheel is modeled individually, with its own sprung mass and unsprung mass. The sprung mass refers to everything that is supported by the suspension, for example, the vehicle body, engine, and passengers. It rides on the springs and dampers, so it moves more slowly and smoothly over bumps. On the other hand, the unsprung mass includes the parts below the suspension, such as the wheels, tires, and part of the suspension arms. These components move directly with the road surface, so they react more quickly to bumps and irregularities. By modeling both masses separately, we can accurately simulate how vibrations and road forces travel through the suspension system and how they affect ride comfort and handling stability. Each wheel also has its own wheel load and experiences both lateral and longitudinal forces. This allows the model to represent how the front and rear tires behave differently during acceleration, braking, or cornering. The center of gravity is defined at a certain height above the ground, which introduces vertical motion effects such as rolling, pitching, and load transfer between left and right sides or between front and rear axles. This model also captures vertical dynamics, including how the suspension compresses and rebounds and how the tire interacts with the road. The tires can still be modeled using nonlinear tire models, such as the Pacheco Magic Formula or Fiala model, to represent real-world grip characteristics. In short, the multi-body model provides a much more realistic and three-dimensional representation of vehicle motion and is widely used in professional simulation software like CarSim or Adams Car. Now, let's look at how vehicle dynamics models are actually used. The use cases. First, vehicle dynamics simulation. We use these models to reproduce realistic car behavior inside a simulation environment. This helps us test control algorithms safely before deploying them to a real vehicle. Second, state estimation. By combining sensor data and the vehicle model, we can calculate how the vehicle has moved, its velocity, yaw rate, or slip angle, even if we cannot measure them directly. Third, behavior prediction. We can predict how other vehicles will move or react, which is essential for autonomous driving and collision avoidance. Finally, we have model-based control algorithms such as model predictive control, often called MPC, and model-based reinforcement learning. These algorithms rely on accurate models to predict future vehicle motion and optimize control inputs in real time. In summary, vehicle dynamics models are not just theoretical tools. They are the foundation for simulation, state estimation, behavior prediction, and advanced control in modern intelligent vehicles. Now that we've learned how to build vehicle dynamics models, let's see how they actually behave in motion. In the following examples, we'll compare how different models, the kinematic single track, the dynamic single track, and the multi-body model, perform when the vehicle is cornering, accelerating, or braking. These simulations show how the level of model complexity affects the realism of vehicle motion. In the cornering example, we'll observe how each model predicts the path of the vehicle's center of gravity and how the slip angle evolves over time. Then, in the over and understeering examples, we'll see how load transfer during acceleration or braking changes the vehicle's trajectory, slip angle, and body motion, including yaw and pitch behavior. Together, these visual comparisons will help us connect the mathematical models we've studied to the physical behavior we can observe in real driving situations. Now, let's take a look at an example of cornering. On the left, we can see the trajectory of the vehicle's center of gravity plotted on the XY plane. Three models are compared here: the kinematic single-track model, KS, the dynamic single-track model, ST, and the multi-body model, MB. At the beginning, all three models produce nearly identical paths. As the vehicle enters the cornering section, the curvature of the path, meaning how sharply it bends, gradually increases. This corresponds to a smaller radius of curvature, or, in simple terms, a tighter turn. But here's an important clarification. While the x-coordinate increases as the vehicle moves forward, that does not mean the turn automatically becomes sharper. The sharpness of the corner is not determined by x itself, but by how y changes with respect to x, that is, the slope, dy dx, and the radius of curvature. A larger curvature means a sharper corner. From that point onward, the kinematic model starts to deviate from the realistic trajectory. This happens because the simplified model does not capture tire lateral forces or inertial effects. The graph on the right shows how the slip angle beta evolves over time. In the single-track model, the slip angle increases almost linearly, while in the multi-body model, it first increases, then reaches a maximum, and finally decreases slightly. This is due to load transfer and tire saturation effects, which create a nonlinear response. In summary, as the model becomes more complex and physically detailed, it reproduces the vehicle's real cornering trajectory and slip dynamics with much greater accuracy. Now, let's talk about understeer and oversteer, two common behaviors that occur when a car turns. On the left, we see the vehicle's trajectory under three conditions: acceleration, coasting, and braking. When accelerating, the path bends outward. This is called understeer. It happens because as the driver steps on the gas, the weight of the car shifts backward. The front tires lose some of their grip, so the car turns less than the driver intends. It feels like the car is pushing toward the outside of the curve. When braking, the opposite happens. The weight shifts forward, the rear tires lose grip, and the car turns more sharply than expected. This is called oversteer. It feels as if the rear of the car is sliding outward. In the middle, the coasting case shows a balanced trajectory. Neither understeer nor oversteer dominates. On the right, we can see the slip angle beta changing over time. During braking, beta increases in the positive direction. That means the vehicle's rear is sliding outward, indicating oversteer. During acceleration, beta decreases, showing understeer, where the front pushes outward instead. In short, understeer happens when the front loses grip, and oversteer happens when the rear loses grip. Understanding this balance is key to vehicle stability and control. Now let's look more closely at vehicle rotation and body tilt under three conditions: acceleration, coasting, and braking. We'll start with yaw, denoted by the Greek letter psi, C. Yaw describes how the vehicle rotates left or right in the horizontal plane. That is, how its heading direction changes as it turns. When the car moves straight, the yaw angle is 0. A positive yaw angle means the car has rotated counterclockwise, or to the left. A negative yaw angle means a clockwise rotation, or to the right. The yaw rate, spoken as psi dot, tells us how quickly the heading is changing over time. This represents how fast the car is turning on the road. Now look at the graph on the left. It shows how yaw evolves under different driving conditions. During acceleration, the yaw rate becomes smaller. The car tones more slowly. This is understeer, caused by the front tires losing grip as load shifts to the rear wheels. During braking, the yaw rate becomes larger. The car turns more sharply. This is oversteer, caused by the rear tires losing grip as load transfers forward. In the middle, the coasting case stays balanced. Neither understeer nor oversteer dominates. Now look at the right graph. It shows the pitch angle, denoted as theta sub s. Theta. Pitch describes how the vehicle body tilts forward or backward. During acceleration, the front end lifts and the rear squats. This is a positive pitch. During braking, the front dips down and the rear rises. This is a negative pitch. The coasting state remains nearly flat and stable. Together, these changes in yaw and pitch clearly demonstrate how load transfer, The shifting of weight between the front and rear affects the handling balance and stability of the vehicle. Now, let's wrap up this lecture with the key takeaways. First, vehicle states go far beyond simple X and Y positions. They also include the yaw angle, slip angle, and tire behavior, all of which define how the car truly moves. Second, linear models help simplify analysis and are easy to compute, but nonlinear and multi-body models capture the real, complex vehicle dynamics that occur during fast or extreme maneuvers. Third, load transfer explains understeer and oversteer. It's the key concept that determines how stable and balanced a vehicle feels while cornering. Next, the Fernet frame, represented by S and D, provides an intuitive way to describe vehicle motion along a path, with S showing the distance traveled along the road and D showing the lateral offset from the center line. And finally, these models together form the foundation for state estimation, simulation, and model-based control, including modern algorithms like MPC, or Model Predictive Control. So in summary, understanding vehicle states and dynamics is the first step toward building reliable autonomous driving systems.